All right, let's dive deep into current electricity. We're talking about the kind that powers our world, not just static shocks.
Yeah. It's all about electrons on the move, those tiny particles that are part of atoms.
So what is electric current, really?
Think of it like a river, but instead of water, it's electrons flowing. They have a negative charge and are drawn to a positive terminal, like a battery. That flow of charge is the electric current.
So it's like a highway with tiny electric cars zooming to their destination.
A great visual. We measure current in amperes. 1 ampere is a massive number of electrons passing a point each second.
Wow, that's a lot of traffic. But isn't it weird that we say current flows from positive to negative, even though electrons are negative? Shouldn't they flow the other way?
You've stumbled on a historical quirk. Early scientists thought positive charges moved, and that convention stuck. We still talk about conventional current from positive to negative, even though electrons move the opposite way.
That's like driving on the left side of the road. It seems backwards. But if all these electrons flow through a wire, wouldn't it become negatively charged?
That's a common thought, but it doesn't happen. The wire stays neutral because for every electron entering, another leaves. Like a revolving door, people go in and out, but the number inside stays the same.
So the wire guides the flow but doesn't get charged itself. What about the wire size? Does the current change if it's wider or narrower?
That's a great question. The current stays the same regardless of thickness. Like water in a pipe, the amount passing per second is the same whether the pipe is wide or narrow.
So current is like the river's speed. The width doesn't change how fast the water flows. Makes sense.
Yeah.
But how fast are those electrons actually moving?
That's drift velocity, the average speed of electrons as they move. You might imagine them zipping, but they're pretty slow.
Really? How do we get instant power when we flip a switch then?
It's fascinating. Electrons bounce around due to thermal energy, even without voltage. But the electric field from a voltage source makes them slowly drift in one direction.
Like a gentle breeze nudging a swarm of bees. They're still buzzing individually, but the whole swarm moves slowly in one direction.
Exactly. That drift velocity is surprisingly slow, often millimeters per second. It's like the electrons are bumping into things in the wire, slowing them down.
Like walking through a packed train station at rush hour. Tiny steps, but slow progress.
Perfect analogy. But even though they're slow, the sheer number of electrons creates that significant flow we call current. We can calculate it using the equation I equals N times E times A times V sub D.
Let's break that down. What are all those letters?
I is current, N is the number of electrons per unit volume, E is an electron's charge, A is the wire's cross-sectional area, and V sub D is the drift velocity.
So the equation shows that current depends on how many electrons are packed in, their charge, the wire's width, and how fast they're drifting. More electrons or a wider wire mean more current, right?
Exactly. It shows how these factors work together to determine the flow. But there's resistance, which tries to hinder that flow.
Resistance, like roadblocks on the electron highway. Tell me more.
Resistance is like friction for electrons trying to move through stuff. It's like running through a crowded room versus an empty hallway. More obstacles make it harder to move.
So high resistance is like that crowded room, making it tough for electrons to get through.
Yeah, and different things affect that resistance, like the material itself. Different materials have different atom arrangements, affecting how electrons flow. Copper, for example, is a great conductor, low resistance, which is why we use it for wiring.
So that's why copper is the go-to. It lets current flow freely.
Exactly. But nichrome, for example, has high resistance, making it great for things like generating heat. Think of a toaster. That heating element gets red hot because of its high resistance.
So it's like purposely making a bottleneck for electrons to create heat.
You got it. Using resistance to turn electrical energy into heat, the wire's length and thickness matter too. A longer wire means a longer path for electrons, more chances of collisions, so resistance goes up with length.
Makes sense. Longer commute, more likely to hit traffic.
Perfect analogy. And a thinner wire, smaller cross-section, is like narrowing that highway, making it harder for electrons to pass. So resistance increases as the wire gets thinner.
Got to give those electrons space. You mentioned temperature before. Does that affect resistance too?
Absolutely. In most metals, as temperature increases, the atoms vibrate more, making them more likely to collide with electrons. That increases the resistance.
So it's like the atoms are getting jittery, making it harder for electrons to get through.
Exactly. But in semiconductors, it's the opposite. As temperature rises, resistance goes down. That's why semiconductors are so important in electronics.
So temperature and resistance depend on the material. Amazing how these things affect the flow. But how do we measure that relationship between voltage, current, and resistance?
That's where Ohm's law comes in, a fundamental principle. It states that the current between 2 points is directly proportional to the voltage across those points and inversely proportional to the resistance.
Sounds a bit technical. Can you break it down?
Imagine a garden hose. Voltage is the water pressure, current is the flow rate, and resistance is the hose width. Increased pressure, voltage, more water flows current. Narrower hose, higher resistance, less water flows, even with the same pressure.
So Ohm's law means if we want more current, we can either increase the voltage or decrease the resistance. To limit current, we do the opposite.
You got it. Simple but powerful, it governs a lot of our electrical world. But with all this talk about current, voltage, and resistance, what about power? What happens to that energy flowing in the circuit?
Right. It's not just about moving electrons, it's about using that movement.
Exactly. That's where power comes in, measured in watts. It's the rate at which electrical energy is used or generated.
So higher wattage means more energy is used or produced over time.
Precisely.
Yeah.
When current goes through a resistor, some energy is lost as heat. That's from those electron-atom collisions. It's Joule's law, which states that heat generated in a resistor is proportional to the square of the current, the resistance, and the time the current flows.
So that's why my phone gets warm when I use it a lot. The battery works hard, pushing current, and some energy is lost as heat.
Exactly. It's natural because of resistance. It's also why old light bulbs got so hot. They used a high-resistance filament for light, but wasted a lot of energy as heat.
Like those old bulbs were inefficient heaters that also made some light. But speaking of light bulbs and other devices, how do these concepts of current, resistance, and power actually play out in the real world?
Well, let's talk about the fuse wire, a small but vital safety device.
Fuse wire. That sounds old school.
You might think so, but they're still everywhere, protecting circuits from overloads. A fuse wire is thin, made of a material with a low melting point. If the current gets too high, the fuse melts, breaking the circuit, preventing damage to other parts.
So it's like a sacrificial part that protects the rest of the circuit.
Precisely. Simple but effective, it prevents things like fires or shocks.
Wow, never realized those tiny wires were so important. What other applications are there?
We talked about incandescent light bulbs, basically resistors that get hot enough to make light. Another is heating elements, like in ovens, heaters, even hair dryers.
So those are all using resistance to make heat on purpose.
Exactly. Nichrome wire is commonly used for this because of its high resistance and melting point.
It's amazing how we can use materials and these principles to make so many different devices. But what about batteries? They seem different from resistors.
Batteries are different. Unlike resistors that consume electrical energy, batteries are sources of it. They turn chemical energy into electrical energy, providing the voltage that drives current.
So they're like tiny power plants pushing those electrons along.
Exactly. But even batteries have internal resistance affecting how they work.
So even the power source has resistance the electrons need to overcome.
Precisely. That internal resistance can cause a voltage drop when the battery is in use, making its output less effective. That's why a battery might seem to weaken even with charge left. Its internal resistance is increasing, making it harder for the electrons to flow.
Wow, so there's resistance inside the battery too. Seems like resistance is everywhere in electricity.
In a way, yes, it's a fundamental property of materials, and knowing how to manage and use resistance is key to designing good and safe electrical circuits.
We've covered a lot. From current and resistance to Ohm's law and power, there's a lot more to electricity than meets the eye.
And we've only just begun. There's so much more to explore about electrical phenomena.
Well, I'm ready to keep going. What else can you tell us about current electricity?
Now, let's look at something that might sound a bit scary, but is actually pretty simple. Kirchhoff's laws.
Kirchhoff's laws. That sounds like serious physics stuff, or you need equations and all that.
Don't worry, no hardcore math. Kirchhoff's laws are just basic ideas about how current and voltage work in circuits. They're like the traffic rules for electrons.
Okay, that sounds more manageable. Tell me about these electrical traffic rules.
The first one, Kirchhoff's current law, or the junction rule, is all about keeping things balanced, the conservation of charge.
Conservation of charge. Didn't we already touch on that with conductors staying neutral?
Yeah, same idea, but now we're talking about circuits. Imagine a spot in a circuit where wires meet, a junction. Kirchhoff's current law says the total current going into that junction has to be equal to the total current flowing out.
Like a busy intersection, the number of cars going in has to equal the number coming out. No cars just vanish or appear out of nowhere.
Perfect analogy. It shows that charge isn't created or destroyed at a junction, just flowing through.
Makes sense. What about the second law?
Kirchhoff's voltage law, also called the loop rule, is about energy conservation. It says that the sum of all the voltage drops around a closed loop in a circuit has to be zero.
So closed loop. So if I trace a path around a circuit, the total voltage change should be zero.
Exactly. It's like going on a hike. You climb up, gain elevation, but when you get back to your starting point, your net elevation change is zero. Same in a circuit, voltage goes up and down through components, but the total change around a loop is always zero.
Like a roller coaster for electrons, ups and downs, but they end up at the same energy level.
Precisely. And these two laws, current and voltage, are super useful for understanding complex circuits. They help figure out current flow in different branches and how voltage is spread across components.
I can see how those would be essential for electrical engineers.
Definitely fundamental tools. Now, we've talked about single resistors, but what happens when we combine them? They can be in series or parallel, and each way affects the overall resistance.
You mentioned that before with power. Series resistors share voltage, parallel ones each get the full voltage.
Right. And the total resistance changes too. In series, total resistance is just the sum of each one, like adding obstacles on the electron highway, making it tougher for current to flow.
So more resistors in series, higher the total resistance.
Exactly. But parallel gets more interesting. The total resistance is actually less than the smallest individual resistance.
Really? How does that work?
Think of it as creating multiple paths for current. Like adding lanes to a highway, traffic flows better, even if some lanes are slower.
I get it. More paths mean less overall resistance, more options for the electrons to get where they're going.
Exactly. And knowing how to combine resistors like this is key for designing circuits with specific resistance and controlling current flow.
Wow, we've learned so much.
Oh.
From the basics of current to Kirchhoff's laws and combining resistors. What an electrifying journey.
It's incredible to think that something as tiny as electron flow has such a huge impact on us. From powering our homes to all our technology, electricity is really amazing.
I've got to say, I feel pretty energized after learning about electricity. Who knew those little electrons were so fascinating?
The more we learn about how things work, the more we can appreciate how amazing and complex it all is.
So next time you switch on a light or charge your phone, think about those electrons, driven by voltage, battling resistance, powering our modern world. Keep exploring, keep asking questions, and stay curious about the electrical wonders around us.